So the speaker is Susanna Zimmermann from Angers University in France. She's going to speak about algebraic groups acting birationally on surfaces over a perfect thing. So please go ahead.
Thank you very much for the introduction, and also thank you very much for the invitation. I'm very happy to speak in front of you, literally on several continents at once. So today I want to talk about algebraic groups by acting birationally on surfaces over an arbitrary perfect field. So depending on your preferences, so for me, K will be some arbitrary perfect field, and you take your preferred one. For many people in my field, that's C, and then R, Q, F of P, what you prefer, but just not FP of T or anything similar, because those are not perfect. And for me, from my point of view, an algebraic surface X over K, this is the same thing as the same surface over the algebraic closure, together with a Galois action. So for me, this is if you think of an affine surface or a projective surface, this is the same as saying I'm very sorry. This surface is given by a polynomial equation with coefficients in K, but you can just say that this is a polynomial equation over K bar, which is invariant with respect to the Galois action. Also. And then in that surface, for me, a curve or a point is I see it geometrically. So for me, that's just a Galois orbit of a curve or a point over the algebraic closure. So to make an example, I have I'm setting myself in P2 and over R. So K is equal to R, and then for instance, I can look at a curve which is x squared plus y squared equal to 0. So this is an irreducible curve over R over C. It has two connected components, x plus iy equal to 0 and x minus iy equal to 0, and the Galois action exchanges the two.
You mean two irreducible components?
Two irreducible components,
connected.
Yes. Connected, yes. So two connected components over C. And here the Galois action is given by the complex conjugation. So the anti-holomorphic involution. Literally, I'm sending xy to, so I goes to minus I. So, so this is here P2 over R. For me, this is the same thing as saying I'm looking at P2C and I'm sending x, y, z. This is the group action x bar, y bar, z bar, where the bar is the complex conjugation. And then, so on this curve, we have a point that is 0, 0, 1, that is a rational point. It's fixed by the Galois action. And I have points, for instance, now I have to check my calculations. So 1 minus I0 and 1 I0, which are complex conjugates. And their union, I see, is a closed point over R, but over C, that's just a Galois orbit. So this allows me to look at the variety over a field that is not closed in a geometric way. And now for me, in the same way, I look at an algebraic group as an algebraic group over a field, as an algebraic group over the algebraic closure of the field together with a Galois group. And I say it acts birationally on a surface. If there is a birational transformation from G times X to G times X, that is of the form I'm sending Gx to G and then something that depends on G on X. This is supposed to be an action. but the action is not defined, may not be defined everywhere. So I want this to be birational, and that means there are dense open sets, U and V, on which this map restricts to an isomorphism. And moreover, I want that the projection of U and V onto the first factor is surjective. So this this will mean that there is no element of G that acts that is nowhere defined. So I want every element of G to be a birational map, almost. So I want this to be an action. So I want this part of my map to satisfy the usual group axioms of a group action whenever it is defined. So I will make a bunch of examples just afterwards. G, when I say G a group, the group may have elements that are not rational elements, right? And if the rational elements, they act, so so each of these for a G, so rho G of something, if this guy, the G is a rational element of the group G, it acts as a birational map defined over my base field. So G goes to rho of G. This induces a group homomorphism from the rational points of my group G to the group of birational maps of X, which are defined over K. So the most easiest example of this is if G acts by automorphisms on X, if it's a subgroup of the automorphism group, and then this here is just an isomorphism, and we can take U and V to be equal to the product. And what I want to do is I want to classify the algebraic groups that act birationally on P2, on the projective space. The projective space is the most simplest algebraic surface. It has many symmetries, and I want to know which ones are algebraic. And of course, I want to classify these group actions up to conjugation by birational maps. So let me make some examples for algebraic groups acting birationally on P2 that are not the automorphism group. So the first example is PGL2 squared, which it's R points. So is the PGL2 R squared, and that's the usual a subgroup of a usual automorphism group of P1R cross P1R. So I'm writing it like this because I want this is for me just a set of real points of this group. And I look at the following birational map that goes from P2 to P1 cross P1, and I just that is composed of the two projections. So I project onto y equal to 0 and onto x equal to 0 on two maps. This is a birational map, and I let G acts on here, and I just conjugate to get some sort of action here. The conjugation will not be an automorphism of P2 because this is not an isomorphism here. And I computed this directly. So if you have an element, if you have this element, that is the two matrices A, B, C, D, and alpha, beta, gamma, delta in PGL2 squared, then what the conjugation gets you, so this acts as usual on P1 cross P1, and if you conjugate back, you get this fellow here. So this is a quadratic map, as you can see, and quadratic maps are not automorphisms of P2. They are not defined in each of these. For each A, B, C, D, alpha, beta, gamma, delta, this map is not defined in at most 3 points, and it contracts between 1 and 3 lines. And in fact, you can just compute which lines it contracts. That's exactly the determinant of the derivative of this map. Okay, so, and that's this polynomial. So you can check, these are exactly, each of these equal to 0 gives you a line which is contracted by this birational map. So this one, this line is, if it's equal to 0, you get, it's contracted onto a point, onto 0, 1, 0. So gamma y plus delta z equal to 0 is contracted onto 0, 1, 0. It's not so this means that this map here is not an isomorphism on this line outside maybe. The same way, so x cx plus dz equal to 0 is sent onto where we have 0, 0 here, so it's sent onto 1, 0, 0. And then the last line, z equal to 0, this is mapped onto axy, c alpha xy, and c gamma xy. But this is, generically speaking, this is the same as oh, I forgot a gamma, c alpha, and c gamma. So also z equal to 0 is sent onto a point. Since this map is a quadratic map, these are all the lines where it's not defined, and outside of these lines, it is an isomorphism. So that's exactly, this is exactly the set of lines where this guy stops being a diffeomorphism. It's the determinant of the derivative, this guy. Okay. So outside of the place where he stops being a diffeomorphism, the action is actually really a group action. So this is this map induces is an isomorphism. This map here, I'm sorry, C is an isomorphism between these open sets of G cross P2. So right. The next example is a similar one. It's a similar one, but instead of taking the subgroup of the automorphism group of this quadric surface, we take another quadric surface over R. So we take the quadric surface given by WZ equal to x squared plus y squared in P3. This is not P1 cross P1 because over R, this is isomorphic to this one, which has real locus to the sphere. So it's not isomorphic to P1 cross P1. The real locus of P1 cross P1 would be S1 times S1. Right? So these are not the same quadratic surfaces. And in fact, from my geometric point of view, this surface Q is just P1 cross P1 endowed with the anti-holomorphic involution with the Galois action that makes bar everywhere, but also exchanges the factors. That's the one. Okay. And now we do the same thing as before. I look at the part of the automorphism group of Q, and I conjugate it onto P2. So I look at now PGL2 cross PGL2, and I lift this involution onto this product. So I put an R form on it. I'm sending AB onto B bar A bar. And then the real points are just going to be this diagonal AA bar. And that's a subgroup of the automorphism group of Q. And a map that leads to P2 or from P2 to Q is I'm sending X, Y, Z just to X squared plus Y squared plus these guys. So that's just W set in these coordinates. And so that's in Q. And if I want to see Q as a P1 cross P1, then So the isomorphism from this guy to this guy would be, for instance, this coordinate corresponds to this coordinate. So from here you go from P1 cross P1. And I can, so my G acts on Q. I conjugate it and I get the birational action on P2. I did not compute this because it's more tedious to compute it, but it's the same example. And geometrically, what it does is, so I go from P2, I blow up 2 points, one I0 and one minus I0. I blow up and I look at the map between, but the line between those two. From here, I can blow up the 2 points that I wrote down. They are 2 conjugate points. Okay. And then on this surface, the pink line becomes contractible. Okay, so these are -1 curves, -1 curves, -1 curves. I can contract the pink line and I go to Q. And now my G acts on here. It will move the pink point around. So G, I can lift the action of G onto this blow up, but already only birational, because since G is going to move around my pink point, G will want to move around my pink curve to another curve. And this is not an isomorphism. Isomorphism wants to preserve -1 curves, and there are only 3 -1 curves on this blow up. So this is you can imagine here the birational action like this. And right, so and you can check that this, if you take some random line in here, you look at its image, somehow it's going to be a 1-1 curve in Q. And then I move it with my G somewhere else and I go back. So I will have, what it will give me here is a conic passing through these 2 points. So my group action sends a line onto a conic. That means it's of degree 2. This is what we had before also. Just in the example before, the 2 points would be 2 rational points, and here there are 2 conjugate points. So this is what it does geometrically. Okay. So third example. Here, my group is going to be a split torus times this group of permutations times an involution. So my split torus, it acts on P2 the usual way. And my sim3, that's just the usual permutation of x, y, z. And then my involution here is going to act as this quadratic map. This is an involution because this you can write as 1 over x, 1 over y, 1 over z. So you can check it's an involution. And I'm presenting you here also what the involution does geometrically. So geometrically, you have this curve is not defined at the common zeros of these 3 polynomials. So that's these 3 points here. And then it also contracts x equal to 0, y equal to 0, z equal to 0, which is exactly these 3 lines. So they're contracted onto these points. And it's an involution, so you can, so these lines, these red lines here, they're contracted onto the red points. And it decomposes into blow-ups and blow-downs. So you can blow up the 3 red points, and then you get a hexagon of lines. Those are all -1 curves. And then on top, sigma just exchanges opposite sides and then contracts the sides. So, so this point would become this, and then you blow down this curve, and you get to this guy. So in this group in G, everybody, so T2 acts by automorphisms, the symmetry group acts by automorphisms, and this guy acts birationally. And it is an isomorphism outside of these 3 lines. So that means this whole group is an isomorphism outside of these 3 lines. And in fact, you can lift this whole group G to, so G acts here, you can lift it onto Y, and here everybody acts as an automorphism, because the torus and the symmetry group, they fix the points that they preserve the set of red points that we blow up, so they lift two automorphisms of Y, and sigma acts as an automorphism on Y, but not on P2. On Y, it just exchanges the curves in the hexagon. Okay, so I'm iterating this example for an example where we don't blow up 3 rational points, but a rational point and 1 non-rational point. So this time, my involution will be given by xz, yz, and then I'm putting here any irreducible polynomial over my ground field. Over the algebraic closure, it decomposes into 2 linear parts, and those linear parts give me 2 points here in P2. And this sigma will be not defined at exactly these 3 points, the common zeros of these 3 polynomials. And then I can again define a quadratic map. Sigma is again a quadratic map that decomposes into blowups and blowdowns. I blow up the 3 red points. I get to a hexagon, and well, I blow down the other 3 lines, and this gives me exactly the way sigma acts on this triangle. Contracts these 3 lines, and there are the 3 red lines here. They are contracted onto the 3 red points. Okay. Now the difference is that we blew up non-rational points. So the Galois group acts. The Galois group exchanges these 2 red points. Fixes this one. So here it acts like this. So this example is exactly the same one as we just saw, only that our surface y's, they are different. They are completely different. And again, so everybody in this H, right? I have a group H, which is just a set of automorphisms of P2 that fixes each of these 3 points. So it lifts to an automorphism. H acts here by automorphisms. It lifts to automorphisms of Y. Sigma lifts to an automorphism of Y, and so just the whole group G lifts to an automorphism, a group of automorphisms of Y. Okay, so until now, do you have any questions? Are you still with me? I don't hear questions, so that's good. I assume that's good. So now, how do we classify these groups? And here, a theorem of Weil, Rosenlicht, Sumigio, and Briand is essential. It says that if we have an affine algebraic group over some field that acts birationally on an algebraic surface, then in fact, by changing the model birationally, we can get to a smooth projective surface that carries the action of G by automorphism. So here, so there's a birational transformation from X to Y. Y is a smooth projective surface, and here the action is birational, and here it is by automorphisms. And I would like to also mention that so the first version of this is by Weil, and he did this for irreducible groups for simplicity, he writes. And then Rosenlicht, he extended it to any amount of irreducible components of the affine group. And for them, the surface Y, in fact, they prove it in any dimension. And for them, the variety Y is just another variety Y. They don't care what properties it has. And then for Sumihiro, he extends, so you can assume, you can always restrict to the smooth part of Y, because the non-smooth part, because it's preserved by G. But then you want, Sumihiro tells you that if G is connected, you can assume that Y is projective. You can get to a projective version of Y. And Briand, he generalized it again for any amount of irreducible components of the affine algebraic group. So this is why all of these names are there. So if we want to...
Maybe something in the statement, so you mean, so Jack, the action on X is a pullback from this action on Y, is what you mean? Yeah,
exactly. It says that any birational, if you have an affine algebraic group acting birationally on an algebraic surface, it actually comes from an action by automorphisms on some birational model of X. Exactly, yeah. So all the examples I showed you there, right? You saw that there is an automorphism group somewhere, and it's not a coincidence. So now that I'm on a projective smooth model of my variety X, it's a very complicated surface. I'm going to start the minimum model program from it to get a minimum model. And I'm going to do this over K, over my field, and G equivariantly. This just means, since I'm over a perfect field, this just means I can run the MMP, but I only contract orbits. I contract the sets of -1 curves that are disjoint, and this set is at once the Galois cross G orbit of curves. So the Galois orbit ensures that I'm doing my minimum model program over K, and this one ensures that I'm doing it G equivariantly, so that if I contract my -1 curves, the G action goes to the next nice model. And so for instance, in the surface that we had just before, which was a Dilbezzo surface of degree 6, and we had an action of the Galois group on it, like this. And the way you would design this by just you choose 2 curves that are disjoint and in the same orbit, and then you can contract them simultaneously. Did I? No, did not. Okay. All right, and if your surface was rational to start with, where you will end up is either a Dilbezzo surface, one of the Dilbezzo surfaces, where you cannot contract anything equivalently with respect to your group action anymore. So all of the -1 curves, they are either the same, they're either conjugate by the group action, by the Galois group, they are not, and then they are not disjoint, or they are in the same G orbit. Or you end up on a P1 vibration, on a conic vibration above P1, and where you cannot contract any components of singular fibers anymore without losing either the property that you are over K, or without losing your the action of the algebraic group. And well, now to classify the groups, what remains to do is to literally write down all of the options of the Dilbezzo surfaces and the conic vibrations, and to check. So G acts by automorphisms of them. So you can check the automorphisms, and depending on which world of algebraic groups you want to stay, you have to check which ones are conjugate. So basically that's the way to go. This is also, if you are working in higher dimension, this is the same way to go, only that your list of varieties at the end is much more complicated, of course. So. Now, what do we know about the algebraic groups acting birationally on P2? So if the field is algebraically closed, this is a very, very long story already, and it accumulates for the finite groups in the works of Dolgachev-Iskovskikh and Blanc around the 09, and then the non-finite groups up to conjugation and inclusion were classified by Blanc in 09 as well, in characteristic 0. So over R, the next nicest non-closed field is the finite subgroups. They are already not entirely classified. So there are partial classifications by Robayo and Jasinski. It works. And if G is infinite, Robayo and I classified the maximal ones. So the groups up to conjugation and inclusion. And in a working project, I'm sorry, the French is creeping. And it is in a collaboration with Jeltsov, Jasinski, and Mangold. We are attempting to classify the involutions over R. So where G is of order 2. So you can see at the level of groups where the classifications is not entirely known yet. And then over an arbitrary perfect field, there is again a partial classification for the finite groups, this time by Dolgachev and Iskovskikh. And for the infinite ones, that's what I would like to present you now. It's a collaboration with Julia Schneider. And then maybe I could add that in higher dimension, there is a classification of connected groups. So in dimension 3, she connected, or well, I'm going to write here maybe x equal to P3. For G connected, this is by Umemura, and then a work by Blanc, Fanelli, and Terpero. They have largely reconstructed this classification, but with the techniques from the minimal model program, where Umemura, this was done in the 80s, uses more analytic methods. And in dimension bigger, we have absolutely no clue. But the connected groups are, finite groups are. There's for G finite, there are partial classifications by Prokhorov and Shramov. And this is
yes.
all over C.
So I have a question, but in higher dimensions, you don't have the results with the 4 names you mentioned before, right?
Yeah, no, in higher dimension, we still there's still this theorem still holds, but and you can still do the minimal model program over K and equivariantly, but your classic, like the minimal models, they are much more complicated. You will get to a Mori fiber space, and you will have so these are vibrations over something smaller dimensional, and the general fiber is a Thano variety. So, and these varieties, they are not classified entirely, which makes the list, which makes studying these vibrations very difficult.
Okay.
Does this answer your question?
Yes, merci.
Okay.
So I have another question about the minimal model program. So I understand that classically, Manin and Iskovskikh only treated those the 2 separate cases where the field wasn't algebraically closed, or when it was algebraically closed, and there was a finite group action.
Mm-hmm.
So this hybrid form that you stated is that written down somewhere?
Yes and no. So it's a small, the hybrid jump is the hybrid form is a small jump from the other two forms. And what you need is that this group here has finite action, so that the orbit of any curve consists of only a finite number of curves. Otherwise, you cannot within the minimal model program, you cannot contract an infinite amount of curves for surfaces. So the version you can do it over K is saying that the Galois group has finite action. So the orbit of any curve is finite. A curve has only finitely many Galois conjugates. And the other part is saying that since your group is affine, the connected component acts, the orbit of a connected component. If you have a curve, the orbit by the connected component is the curve itself. So the orbits of curves are also only finite. And then you put the two together, and it's actually just this property that you need to do the GMMP, the minimal model program. You need to make sure that your orbits of curves are finite. That's all you need. And this is, in some sense, written down a little bit in the book of Collard and Mori, where they say for finite groups, this is fine because finite groups have finite action. But since both of these people have finite action, actually the same holds what they are saying. Does this answer your question?
Thank you. Yes.
Okay.
Thank you.
Right. So let me first look at the conic vibration case. So here I'm first doing this case and then this case. Okay, so this is it's more like a 1, 2. So for the conic vibrations, it turns out that there are only 2 cases. So this is if your automorphism group is infinite. That means this is the automorphism group of Z K bar endowed with a Galois action, and its rational point is exactly the usual automorphism group over K. So if this here is infinite, then these conic vibrations, the minimal conic vibrations, they have 2 sections that don't intersect and that have negative self-intersection. This is basically because you're working over a rational surface, and you can, over the algebraic closure, you can always go down to a Hirzebruch surface. Now, the Galois action gives you 2 options. Either it exchanges the 2 sections or it doesn't. So if it preserves each of the 2 sections, you can choose to contract some of your components, and you will end up on a Hirzebruch surface here. At the same time, so maybe your automorphism group descends to an automorphism group of Fn, and then your minimal surface is actually, your set was Fn. But if this is not the case, if this set is really minimal, this means that you have at least one automorphism that exchanges one of a component of a singular fiber. And in fact, you can construct an involution of Z that exchanges all of the components at the same time. Otherwise, you could contract some components equivariantly. Okay, and then geometrically, you can see that actually your set is obtained by coming from a Hirzebruch surface, and you blow up a bunch of points that are on on a section that is not a special section, that has intersection, self-intersection plus n. And that means you blew up 2 endpoints on this section, and they have to be, they're a set of Galois orbits, so a set of closed points. And you can compute more or less explicitly what is the automorphism group. The action of the automorphism group on Z gives you an action on P1, which gives you this exact sequence here. And the same, of course, for the rational points of these groups. And the only thing is that maybe you have to check whether or not anybody that is an K-automorphism of P1 preserving the image of the singular fibers is actually coming from a K-automorphism of Z. So this is the only thing to check. Now the other option is that your Galois group exchanges the 2 -n sections. Okay, so this means over K, your minimal model is not going to be a Hirzebruch surface, but it turns out that you can always contract some components and arrive on a minimal model, forget the G action, where the two sections become -1 curves. So this is a Del Pezzo surface of degree 6. And you can contract the 2 -1 sections, which are conjugate, onto 2 points, and you will arrive on a quadric surface. And the vibration that you had on here is just the 1-1 curves passing through the 2 points. And since I'm working with rational surfaces only, all of these quadrics, they have a bit the same form. They're given by a polynomial equation like this. And you can, just like on the left-hand side, what you can do is you can construct, since this vibration here was minimal, you can construct a involution of the surface, the blue guy, that exchanges all the components in the singular fibers at once. So you can, the same way as in the other vibration, you can compute who is the automorphism group of this offset of this vibration, depending on the quadric surface this time. And in any case, what you get is that, so here, you have this part of the exact sequence. So you get that the automorphism group is a semi-direct product of the kernel of the morphism from odd Z to odd P1 plus times whatever is the image here. And then to compute the kernel, you know that you have an involution up on Z on the surface, and you also know that the automorphism group, so this Z, the surface Z, has exactly 2 -n sections. So these are the only ones. So the automorphism group acts on it. It induces a map to Z2. This map is surjective because you do have an involution actually exchanging all the components, exchanging the 2 sections, and then it turns out that the kernel is some torus, some sort of torus, not possibly non-trivial, non-split torus. Okay, so let me go to the Del Pezzo surfaces. Right, so here is the crucial part for me that I'm looking at infinite. One of the crucial parts, I'm looking at infinite algebraic groups acting on P2. And for the Del Pezzo surfaces of degree 5 or smaller, the automorphism group over the algebraic closure is finite. So these Del Pezzo surfaces do not appear for me in this case. So we only have to check what is the automorphism group of the beta surface of degree 6, 7, 8, and 9. And this is rather straightforward, mostly. So for degree 9, we are rational, so it's only P2, we know it's automorphism group. For degree 8, this is either a blow-up of P2 in a rational point, and then we know the automorphism group. It conjugates to an automorphism group of P2, or it is a quadric surface, and since, so it's a K form on P1 cos P1, and since my surface is rational, they all look like this. They are all like this for some polynomial, quadratic polynomial. And since they are rational, they are this polynomial. It is the minimal polynomial of a quadratic extension of K, and the isomorphism class of this, the K isomorphism class of this extension determines the quadratic form and vice versa. Okay. So, and then we more or less know its automorphism group. And for the beta surfaces of degree 7, they're blow-ups of quadratic surfaces in one point or blow-ups of P2 in 2 points, but in any case, they have 3 - 1 curves that are permutated by the automorphism group. So we know its automorphism group as well. Okay, so this leaves the beta surfaces of degree 6. And the beta surfaces of degree 6 have 6 - 1 curves that are in a hexagon, and the Galois group acts on this hexagon. And a priori, so that leaves you all of the options. That gives you 9 possible K forms on like 9 up to exchanging, rotating the hexagon. This gives you 9 options that I listed you here. So the first one, let me go through them quickly. So the first one is just the trivial action, and you can contract 3 disjoint sides and you end up on P2. So this is P2 blown up in 3 rational points. And then I have 2 involutions that are reflections, this one and this one. And we can contract the blue curves, they are disjoint, and we end up on a quadratic surface on this one or this one. We have a rotation of order 2, the third guy, this one. And again, we have 2 disjoint sides that we can contract, and we end up on P1 cos P1. So now we have a Klein 4 group, inner group, and then also here we have an orbit that is consists of 2 disjoint sides. We can contract it, and we end up on yet another quadratic surface. Then we have a rotation of degree 3. We contract 3 of the 1 orbit of the sides, and we end up on P3, where we blew up a point that is a Galois orbit with 3 elements. We have a rotation 4 to 6, and we can contract absolutely nothing over K. We have the symmetry group of order 3, symmetry group of 3 elements. We contract an orbit, we end up on P3, where we blew up yet another point of degree 3, and then we have the whole group, we can contract exactly nothing. So in each of these cases, one can arrive at computing the automorphism group of the surface, and you can, for each of these cases, you can actually find a field over which the surface is realized as a rational surface. So they all exist over some field. Okay. And the way you compute the automorphism group is just by, the automorphism group acts also on the hexagon because it permutes the -1 curves. And then you need to check which symmetries are actually verified by automorphisms, and you need to check the kernel of that action. The kernel is going to be some subgroup or some form of a torus action, of a torus. So these are all the subgroups, infinite algebraic subgroups. Infinite algebraic groups acting on P2 that you get. So this is the short version of the theorem over a perfect field. Infinite algebraic group by acting birationally on P2 is up to conjugation and inclusion. Is an automorphism group of one of the surfaces that I just presented to you. So either P2, a quadratic surface, a Hirzebruch surface, a Betzel surface of degree 6, or an exceptional conic vibration with at least 4 singular fibers. And so the K points, so the actual automorphism groups of these surfaces, they are actual subgroups of the cremona, of the group of birational maps of P2. And they are also all maximal except in some cases. And this is in the cases, the first cases where they are not maximal, they are here. This is simply because actually the whole automorphism group of one of these surfaces, of each surface, preserves the blue lines that I'm giving you. And so the whole automorphism group is actually conjugate to a subgroup of the automorphism group of a quadratic surface. The second case appears only when my field has only 2 elements. And that's because in that case, the automorphism group of these 2 surfaces is so small that it has fixed points that are in general position. I can blow them up, contract something equivariantly, and then I can embed my automorphism group into the automorphism group of another little bit of surface. So I was, so here I gotta say, when we made the list, I really expected this part, and then when we arrived at this part, the field of 2 elements. It's nice. Something interesting happens with it. Right. So this is all I wanted to present to you. Thank you very much for your attention.
Thank you for the talk. So we clap online, so that's it.
Cool.
Questions, comments?
So
you can use the chat.
I do have a question.
Yes, please go ahead, Kirill.
So you described this nice example of Delpets of degree 6, but it's also known that it's very much related to because it's a toric variety, right?
Mm-hmm.
And so can you say something more general about the toric variety case? Like there's some nice combinatorics, so I don't know, what one can say about this automorphism.
So I'm for the Betzel surfaces of high degree that are toric varieties.
No, I mean rather maybe higher dimension cases.
In higher, yeah. So I think in dimension 3, the classification by Omimura, and that is mostly reproduced by Blanc, Fanelli-Terperot. I think there are cases where they use toric invariants to determine that an automorphism, a group, is not maximal, or that it is maximal. Because if you have a fibration, say the bits of fibration over P1, you can the fact that you have a fibration and that you know your fibers are toric varieties does give you a lot of information about the automorphism group of that vibration. I don't, for the classification of algebraic groups of BRPN in general, it's over C that the maximal tori, they're all conjugate. So the tors of maximal rank, there's just one basically in the Cremona group. It's the usual one. This is a result of I feel very embarrassed because I cannot pronounce the name. It's a mathematician who I recently read that he died, so I feel even worse of not being able to pronounce his name properly. It's by Birational. I'm sorry if I feel embarrassed. So this is an older result. Birational. I'm sorry. So this is by him. And this is true in any dimension. So the tori, the maximal torus in the Cremona group, there's just one. They're all conjugate.
Thank you.
Other questions?
So if one were to classify two-dimensional homogeneous spaces for algebraic groups, how far would that be from your classification?
Oh, I am not sure. So the classification, if the homogeneous spaces are rational surfaces, then the classification is really not far. It should be
because most of your actions have a dense orbit.
Exactly, yeah. All of my actions have a dense orbit. So I would say if they are rational, then this would give you back the same classification. At least part of the, so that this would give you part of that classification, I assume. Or yeah, but then there are lots of quotients that are not rational, I presume. So then you would have to attack the classification somehow. If you wanted to go this way, at least you would have to attack it a bit differently.
Okay.
What is known about the classification of homogeneous spaces? I assume
so
a
no,
lot,
I mean, the questions are for you. We could ask Michel Brion, of course, but it's not the right place, I see. Okay.
So yeah, okay, homogeneous spaces that are surfaces, the classification that we have here would be part of that classification, but of course there are many more. So because this is really restricted to rational surfaces. I'm using this very strongly.
Okay.
I don't know more.
One last question, possibly. Okay, no. So thanks a lot, Susanna. So I'm just telling you that the seminar continues next week, same time, with Sasha Vishik. Okay, so see you next week, and thanks again.
Thanks a lot for the
Thank
invitation.
you.
Have a very nice day or evening, depending on where you are.
You too.
Bye-bye.